Continuing on with our final exam review series where I help Selena Sanchez, a fellow YouTuber, review for her final. Now we'll be going over limiting reactants and so much more in this video, and the main example I will be using is from my step-by-step limiting reactant notes. Go to melissamaribel.com or use the link in the description box to buy the notes and follow along. All right, let's go over limiting reactants. For right now, let's just go over what a limiting reactant is. So let's make some coffee. What? Coffee, my favorite. All right, so what we're gonna be talking about is which one is the limiting reactant. So how I like to look at it is I like to look at it as where it's like ingredients, right? We have two different ingredients. Those are our reactants, two different reactants. And our product is whatever we're trying to make. So our cup of coffee. And 1 cup of coffee, we have to have 1 cup of beans and 1 cup of milk. That gives us 1 cup of coffee. But we initially have, in our pantry or in our fridge, we initially have 20 cups of beans and 2 cups of milk. So what we want to figure out is which one is the limiting reactant, meaning which reactant or ingredient isn't going to allow us to produce as much coffee as possible. All right, so if we were to look at this and just looking at, let's say, the first one, so let's see how many cups of coffee we can make from each ingredient is the first part. Where for our first ingredient for the beans, if we had 20 cups of beans and let's say we magically had enough milk, also 20 cups of milk, then we could make 20 cups of coffee. Good so far. Mm-hmm. And then next, if we were to just look at the milk now, well, the milk, we could only make 2 cups of coffee. So whichever reactant produces the least amount of products, that's going to be the limiting reactant. So in this case, our limiting reactant would then be the milk. And I know it's obvious from the beginning, but it's not going to be as obvious for, actual chemical reactions. So that's what I want you to write down and to think about is, if we want to write this down, a limiting reactant produces the least amount of product. Mm-hmm. Whatever the limiting reactant produces, that's your theoretical yield. So your theoretical yield is whatever your limiting reactant produces, if we also want to add to that. So theoretical yield is whatever your limiting reactant produces. Cool. So then for this example, our limiting reactant would have been the milk. Our excess reactant, which I'm going to call ER, would have been the cup of beans. And then our theoretical yield, I'm going to call it Theo, that is the 2 cups of coffee because that's whatever our limiting reactant produced. This 20 cups of coffee is irrelevant, all right? And the reason why it's irrelevant is because we don't have enough cups of milk to be able to produce this. And we'll go into this further, but I just want you to know that there's only going to be one possible answer for grams of your product, all right? And we'll get to that. So good so far. Is this making some sense? Mm-hmm. All right, let's get to the chemistry. So first things first, let's figure out our limiting reactant. And how we want to do this, how we always want to approach this, is you're always going to go from grams of each reactant to grams of your product. So that's step number 1 for your limiting reactant, is go from grams of your reactant to grams of your product. So it's stoichiometry. And then here we have 2 different reactants, right? So we're literally going to do this twice, and we're going to go from grams of this reactant to grams of product. And then, by the way, I know there's 2 products. It doesn't matter which product you choose. Each one is going to give you the same result. As long as when you do this, you go to the same product, meaning if I were to go from grams of this reactant, then I go from grams of product, I have to go to iron. And then let's say for this one, if I go from grams of reactant, I also have to go to iron. I can't go, this reactant to this product, this reactant to this other product. I can't jump around. Mm-hmm. With me?
Yeah.
I'm going to have you try this. And how I want you to try this is stoichiometry, all right? Breathe, it's okay. This is just stoichiometry. All we're doing is we're going from grams of our first reactant, which is this, right? So we know we're going from grams of Fe2, and we're given that, correct? So that's what we're initially given. Mm-hmm. And then we're going to go from grams of, let's say, which one do you want to choose?
Iron.
Okay, perfect. So we'll go to grams of iron. So this is what we're trying to do. Set this up. You got this? You got this? Pause the video and try this question out because it's most likely on your final.
Yeah, I don't know what I'm doing.
What do you start off with?
The grams of Fe2O3,
Cool. They're up here.
167.
So you got that. And then if we don't know where to start, what do we convert to?
Moles.
Moles. Good. How do we convert to moles?
The molar mass.
Yes. And the molar mass of iron, 55.85 is irons. So define that.
So 159.7.
Correct. And that's going to go top or bottom?
The bottom.
Good. What goes on top?
1 mole.
Perfect. What's next?
Um,
So our grams cancel, right?
yeah.
We're at moles of iron oxide. We're trying to find moles of iron, not iron oxide. So what's next?
Mole to mole ratio?
Beautiful. Keep going. So what's our mole to mole ratio?
I don't know.
Where do we get our mole to mole ratio?
The balance equation?
Okay. What is our balance equation telling us? How many moles of iron oxide do we have?
1.
Good.
So is it 2 over 1?
Perfect. So we have 2 moles of iron on top and then 1 mole of iron oxide on bottom. And then we're trying to get to grams. So what's our next step?
The molar mass?
Good. Beautiful. 55.85 is our molar mass of iron. So this is what we should have gotten. And then this is kind of how I want you to keep thinking about it, okay? So I know at first it feels kind of painful, right? To kind of like, I feel like I'm squeezing it out of you. But it's all just to get you to think about each part and every single conversion factor that I was talking about in the beginning, right? Is it kind of making more sense what I meant by like a puzzle piece where you have to figure out, okay, now I have to go from moles of this to moles of that. What do I use? And you keep on doing that. And it's literally the same things that you're going to keep on using for these types of questions. So like, and it really is the same process going from grams of one reactant to grams of another. Your moles are going to be in between. That's really it. You're always going to do the same thing. You're going to go from grams to moles of the same compound using the molar mass, and then next to change the compound, mole to mole ratio using our balanced equation, and then last will be our molar mass of whatever we're now finding. So it's the same sort of concept each time whenever we're going from grams of something to grams of something else. Making sense?
Yeah.
We're going to do it again because we have to. So, and I say that because we have 2 reactants, right? So we just found the first reactant. We're going to do the same exact process, except now we're going to use this second reactant. So after you do the math, this is what you would get for grams of iron. So what this is so far telling you is this reactant is going to produce this amount of product, okay? We're going to do this again. This time, I want you to do this same process just with our second reactant. So same process, just using the second reactant, and we have the grams. So go for it. Number 1 question asked on the final. So try this one out.
I'm stuck. I don't know what I'm doing.
Walk me through it. What do you have so far?
85.8 grams of CO times 1 mole of CO over 28 grams.
Good so far. Keep going.
That's all I know how to do.
What do we learn next? What comes next?
The mole to mole ratio.
Yes.
But I don't know what that is.
How do we find it?
Is it the 3 on the bottom?
There you go.
But I don't know what's on the top.
What are we trying to get to?
I don't know.
So this went from going from grams of each reactant to grams of the same product. What was the product that we were trying to get to last time?
I don't know.
With our limiting reactant, we're always going to go from each reactant to the same product, okay? And we decided that we were going to go to iron. You could have decided that it was CO2, but that would have been for both of them. So we decided we're going to go from grams of iron oxide to iron, which we did in the first step. And then now what we're doing is we're going from grams of carbon monoxide to grams of iron. Does that make sense?
Yeah.
So then what should go on top here?
The iron?
Correct. How many moles of iron do we have?
2.
All right, now that cancels, what's our next step?
The converting it to grams?
Correct. So what's on top, what's on bottom? It's okay if you don't know the molar mass of iron. I just want to know, is grams on top or grams on bottom?
Top.
Yes. 55.85.
Okay.
Yeah, you're going to be given a periodic table, so I'm not worried about that. What we're focused on here is just the setup. I just want to help you, I want to see where the disconnect is, and then what I'm seeing right now, it's the multiple ratios. I see that's what's tripping you up, all right?
Yeah.
And it's tends to be this initial step, the second step. So at least now it makes sense that you're not just going to look at this question and be like, nope, see ya, I'm done, Always start with changing it to moles, which is what we got, which is beautiful. And then next, once you're at moles, think, do I want the same compound? Do I want the compound of CO? No, I don't. I want Fe, right? So then from there, I have to do a mole to mole ratio based on the balanced equation. It's starting to make some sense.
Yeah.
All right, so when we do all this, this is going to give us, so this is our second reactant, and this is going to produce this amount of product of iron. So what this is essentially going based off of was, remember the coffee example where we had two different ingredients or two different reactants, the coffee beans and the milk. So that's what we're talking about here. We're trying to now compare and see which one of these reactants is going to produce the least amount of coffee or the least amount of product, which is Fe. So whichever produces the least amount, and I'm just going to say it again. So whatever produces the least amount of product, right, is our limiting reactant. So then I'm going to compare what I produced from both of these reactants. And our first reactant produced this amount of product. Second produced this amount of product. So which reactant is our limiting reactant?
This CO.
Perfect. Because it produced the least amount of product. So that's how you're going to instantly know, well, it's not instant, but that's how you're going to know what your limiting reactant is.
Mm-hmm.
And then from there, we also know what our excess reactant is. So our excess reactant obviously is going to be the other reactant. So iron oxide would be our excess reactant. I'm going to keep going with this question. So these questions on your finals tend to be limiting reactant, then it goes into excess reactant, goes into theoretical yield, percent yield. It's like a common question, but that's why I'm preparing you so you don't go to your final and be like, what is this nonsense? All right. So yeah, I'm prepping you because, like I said, I've seen this on like every final I've ever seen. I'd be shocked if they didn't put it. But this next part is finding the theoretical yield. So we technically already found the theoretical yield. Do you remember what the theoretical yield is? It's fine that you look at your notes. So I had you write them.
It's a CO.
So that's our limiting reactant, though.
Yeah.
Our limiting reactant was the CO. Our theoretical yield is whatever that limiting reactant produced in product. So that's what I want you to know. Theoretical yield is what the limiting reactant produces. I'll get to that little thing in a second. But we did that already, where this doesn't matter, and I'll get to that in a second, but this is what we're looking at. This right here, this amount is our theoretical yield because CO was our limiting reactant. This doesn't matter because we can't actually produce it, right? We were limited. We didn't have enough CO to actually produce this amount in grams. That's how I know this is irrelevant. It served its purpose. It was only there to help us figure out which reactant was the limiting reactant. All right, so there's only going to be one theoretical yield. So in this case, I know this is going to be my theoretical yield. And then something else I just wanted to note was other ways to write the theoretical yield or even say the theoretical yield. Sometimes they won't actually just straight up say it. They're instead going to say, find the maximum amount of product produced. And that's your hint of it saying, oh, it is the theoretical yield, right? And then another way they can also say it is what's the minimum amount produced. And max or min theoretical yield is the only thing that you can produce, all right? That's what I want you to think of. They're trying to trick you when they're stating that. All right, so if you want to make a little note of that, just letting you know whenever they're asking for the maximum amount of product, they're asking for the theoretical yield, or even the minimum amount of product. I'm going to keep going. So that's our theoretical yield. So I'm going to keep going. Okay, this next part is very important. I'm going to go back to the coffee example, just thinking about it. So we had 20 cups of coffee beans initially, and then we also had 2 cups of milk. Your limiting reactant is going to be completely used up. right? Because the theoretical yield in that case was we could only produce 2 cups of coffee. Remember that example? Yeah. So if we could only produce 2 cups of coffee, that means that our excess reactant is going to be the coffee beans, but we want to know how many cups of coffee beans do we have left over? That's the concept here, okay? So when this is asking you to find the excess reactant and how much is left over, it's basically saying that. It's saying how much, well, first you have to figure out how much did you use in the overall reaction, and then you're going to subtract that from the initial given value in grams that you were given, okay? So, and I have a formula for that, so don't worry about it. But what I want you to just know, okay, well, we know our excess reactant, that's the iron oxide. The first thing, and do I have I have the formula, it's gonna show up soon in the second step. And you can write that down. But what I want you to know where we're gonna begin or where we're gonna start is with the theoretical yield. So when you're trying to find the leftover of the excess reactant, you're always gonna go from the theoretical yield to the amount used of the excess, okay? So you can make a note of that if you'd like. I want to say I have it. Yes, I do. Okay, beautiful. That's what I wanted to show. So this is always for finding the leftover of your excess reactant. Start with your grams of theoretical yield and then make your way to grams of the excess reactant. Is this making sense?
Yeah.
If it's not, please tell me, seriously.
I just need to see an example.
I'm going to start off with the theoretical yields, and this is what we found before, right? This was our theoretical yield. I'm going to make my way to our excess reactant, which we said was iron oxide. So first things first, just converting this to moles, right? So I'm just converting this to moles. This is the molar mass of iron. Next, once these two cancel, I now can do a mole to mole ratio. So I can have my mole to mole ratio from my balanced equation, which was here. So I know we have, 2 moles of iron is going to go on bottom. For every 1 mole of iron oxide will be on top. And then from there, I see, okay, well, my moles of iron and iron cancel. I'm now at moles of iron oxide. And then lastly, I can then get to the grams. And what we're finding is we're finding the grams that's used up in the reaction. All right, so this is how much we use to actually help make this amount of product. So I know this is how much I actually used. It's not my leftover, it's not the excess. To figure out how much is left over, I have to do this. So to figure out the leftover amount, you're going to take your original amount that was given in the question, and you're going to subtract this by what we just found, which was the amount used. Making sense?
Kinda.
Let's go back to the coffee idea, where our limiting, our limiting reactant was the cups of milk, right? The 2 cups of milk. And our theoretical yield was 2 cups of coffee. Right, that's how many cups of coffee I can produce is 2. So I start off with the 2 cups of coffee. And then what I would do next is I'd say, okay, well, in my 2 cups of coffee, and we don't even necessarily have to do this math, but in the 2 cups of coffee, every single coffee, like 1 cup of coffee, we have 1 cup of beans and 1 cup of milk, right? So in that case, how many cups of beans did we use to produce 2 cups of coffee?
2.
Exactly. Yeah, I know it sounds ridiculous, like no duh, but it's not as simple here. This is how much we used. This is the representation of that 2 cups of beans, of the coffee beans. All right? This is how much we used. Now we're trying to figure out what's left over. So if we started off with 20 cups of 20 cups of coffee beans, then I would then subtract that by the amount used, which was the 2 cups of coffee beans. So then I'm left over with 18, right?
Yeah.
So that's why I had to go through this whole entire concept of I'm going to start off with the grams of theoretical yield, and then I have to make my way to the grams of my excess reactant, which is going to give me how much I used in the reaction. From there, I then have to subtract that from the original amount that was given in the question. And if we went back to the original question, they gave us 167 grams of our excess reactant. Subtract that by the amount that we just found, and that's going to give us 4, right? That's going to give us 4 grams of iron oxide. So that's going to be how much is left over. Does that make sense?
Yeah.
Next up, percent yield. So percent yield, you've seen percent yield in your lab. And a lot of times people it's never really explained, at least in my case, I remember that percent yield was never explained too well as to what in the world it even is. You were just asked to find it. So what percent yield refers to is I want you to think if you were to do an experiment, and let's say this is my beaker, sure. All right, so if this is my beaker and I'm trying to pour something inside my beaker and create and actually have an amount of product, if my theoretical yield is what I make in the actual experiment, or that's what I physically do. My actual yield is what a scientist, or in like a perfect scenario, is actually produced or should have been produced. Does that make sense? So theoretical yield is what, like, let's say that's what you make in the lab. And then versus your actual yield is what a machine would end up giving you, and it would be perfect, okay? So if you figured out that your percent yield was, I don't know, 65%, that means that you accidentally spilled something. That means something could have been, actually, it's pretty much that. This goes back to like errors, right? This means that maybe something evaporated. You didn't produce the correct amount of product. Now, if you have too much of your percent yield, like let's say if you had like 110%, then that means it's contaminated. Your product is most likely contaminated, and something went wrong. So that's how percent yield that's what it pretty much means. It's telling you how close are you to the value, how close are you to actually have produced the correct amount of product. Yes? Make sense?
Yeah, so I know it's the actual divided by the theoretical, but is it is it 72.3 divided by like one of the answers or one of like...
What was our theoretical yield?
Yeah, that's the question. Is it the 114 or is it the...
It's the 114 because that's what our limiting reactant produced.
Okay.
So we should have gotten this setup, right? And then I don't know if you've heard me say this before, whether in a video or something. This is how I memorize it. Percent yield is where it's at. It's the easiest way I could think of. But in the case that you forget it, just have it help you. But yeah, percent yield, that's how we would look at it. So cool. Then multiply by 100 since it is a percentage. And then we got 63.4%. All that means is this experiment didn't go well. Something got spilled, something got evaporated, or something like that. Some error occurred. But okay, I think we're okay with percent yield. This is another type of question. All right, so this other type of question, sometimes they won't ask you for the percent yield. Instead, they're actually going to give you the percent yield. And instead, they're asking you to find the actual yield. So this is what we're going to do. You're going to use the same formula. All right, so...
Do you just multiply 82.5 times 74.8?
Basically, yeah. After you divide by 100, yes. Perfect. Yeah, divide by 100 first, then we'll multiply. Beautiful. You just plug it in. Simple enough. So percent yield seems to be fine. I think it's mostly just the stoich part, the stoichiometry part that we need to practice. And we will. You're going to get it. You really figured out a lot further. Actually, in the beginning, right? You did those 2 questions on your own. That's improvement. You would have walked away before, but I'm not allowing you to, so. I always see this topic on final exams. So if you would like more practice, I recommend checking out my detailed notes on limiting reactants by heading over to melissamaribel.com or clicking on the link in the description box. And when you're ready, click here to start reviewing Molarity.